I'm Xiaoyu Chen, a PhD student from the Southeast University, and now let me introduce our research on defense against the cache-side channels in speculative executions. And my presentation today will be divided into 6 parts. Let's begin with the first part, attack background. Special attack is a serious vulnerability of speculative execution technique in modern high-performance processors with an extremely broad impact. Attacker in special attack could exploit the misspeculation to execute some instructions that violate program semantics, which involves accessing secret data. And during this period, the states of microarchitecture components are accordingly changed. And attacker could exploit these changes to establish the microarchitecture side channel to leak secret data. Among all microarchitecture side channels, the cache side channel is the most practical method of data leakage. The combination of speculative execution and the cache side channel could allow attacker to leak arbitrary data from the victim's memory space. The establishment of cache side channel could typically involve 3 forces. In force 1, attacker typically aims to make the monitored cache line into a known state. In the most common cache side channel, based on the occupancy states, based on the changes in occupancy states of cache line, attacker evicted the monitored cache line to make them under cache missing state in force 1. And if in force 2, victim performs some memory access operations related to secret data that reloaded the monitored cache line to the cache. In force 3, the access time of this cache line will be shorter since there is a significant time difference between accessing cache lines under cache hits and cache misses. So attacker could exploit such time difference to probe victim's memory access pattern and thereby leak secret data. And based on how attacker evicts the monitored cache line, this type of cache-side channel could generally divided into flush-based attack and conflict-based attack. And there have been many related related defense solutions proposed, such as serializing instructions, invisible speculation, and selective speculation. However, these solutions to address this serious vulnerability are not practical since due to their significant performance and hardware resource overhead. So furthermore, most of the hardware defense solutions lack real hardware prototypes, making them insufficient for real-world application. So to address these issues, we aim to design a defense work with low overhead and has its own hardware prototype. We focus on eliminating cache-side channels in speculative execution established by flush and conflict-based cache-side channels, as we introduced in the background. And before we design our scheme, we need to know that for a defense solution, the larger the scope of protected instructions and the longer they are protected, the more dependent instructions will be blocked and the great overhead will cause. So to reduce the overhead of a defense solution, we need to consider 2 aspects. The first aspect is the protection scope, which speculative loads should be protected. Do all speculative loads could be exploited by attacker to establish cache-side channels? Let's return back to the establishment process of the cache-side channel under our threat model. We could observe that the cache lines that are exploited to leak data by the attacker must be under cache missing state in force 1, so that the victim's speculative loads, which reload these cache lines, could change the cache's occupancy state. During this period, the victim's speculative loads definitely cause cache misses. Our experiments results show that the decache miss ratio are significantly higher in spectral attack exploiting conflict-based cache-side channel compared to the normal program. We referred so under our threat model, the speculative loads causing cache misses are considered unsafe and should be protected. We referred to them as muscle. And the second aspect to consider is the protection duration. Specifically for a load, when we need to protect and deprotect. According to the attack attack principles of spectral attack. During speculation window, the younger loads entering real buffer are executed speculatively along the predicted path. These loads, which might be exploited by attacker to access secret data, need to be protected, and we need to deprotect once the processor could verify this speculation, since we do not need to protect the loads under correct speculation. It's important for reducing the performance overhead, since most speculation it's important for reducing performance overhead to lift the protection timely, since most speculation are correct under normal program. Therefore, the loads within speculation window need to be protected, and the speculative loads under correct speculation need to be deprotected once the speculation window ends. We determine this specific protection duration based on the conditions for the start and end of these speculation windows caused by different variable speculation sources within processor, including control flow prediction, memory access order prediction, and value prediction. And based on these design concepts, we could proceed to design our defense scheme. According to our previous discussion on protection scope, we exploit the route buffer, which stored the information related to all dispatched instructions to design the RISC-V unsafe mask. The RISC-V unsafe mask is designed to track the speculative status of instructions within processor based on the conditions of for the start and end of different speculation windows within processor. And under multi-bank RISC-V architecture, which is commonly employed in superscalar processors, there is a one-to-one mapping exists between the RISC-V rows and the bits of RISC-V unsafe mask, and the value of each bit in the RISC-V unsafe mask is jointly determined by the instructions in all banks of that RISC-V row, so that the RISC-V unsafe mask bit could be 0 once all instructions in that RISC-V row are not within the speculation window. Otherwise, the RISC-V unsafe mask bit will be set to 1. According to our previous discussion on protection scope, we need to protect the speculative loads causing cache misses. So based on the working principle of a load under cache miss, we focus on the other microarchitectural component called line fill buffer, abbreviated as LFB. LFB was in conjunction with MSHR, temporarily stores retrieved cache lines by loads and cache misses, allowing cache eviction and refilling to occur in parallel. We exploit the characteristics of line fill buffer to introduce a security check mechanism that was in conjunction with the RISC-V unsafe mask. And our defense scheme, when MSHR sends a request to the low-level cache of memory to retrieve the missing data of loads and cache misses, the response data cannot be refilled into the cache directly. Instead, it should pass through the security check mechanism. Only when the security check mechanism determines that the requested load is not a muscle, which is indicated by that the corresponding RISC-V unsafe mask bit being 0, could the data be refilled into the cache. When the corresponding RISC-V unsafe mask bit being 1, the security check mechanism should wait for the update of the RISC-V unsafe mask bit. And during the waiting period, the MSHR can simultaneously request data of muscles from the low-level caches of memory, so that when the speculation is subsequently verified as correct and the corresponding RISC-V unsafe mask bit being reset to 0, the requested data can be refilled directly from the line fill buffer instead from the low-level cache of memory without causing too much delay. And so under SpecLFB, the victim's speculative load and cache miss will be seen as a muscle, and the cache lines requested by muscles cannot pass through the security check mechanism in line fill buffer to be refilled into the cache. Therefore, in phase 3, attackers cannot probe any access time differences. We also conducted comprehensive experimental evaluation. SpecLFB is both implemented in the RISC-V code SonicBOOM and x86 out-of-order CPU model in Gen5 simulator, and SSE-RV and CT serve as our comparative schemes for RISC-V and x86 architectures respectively. And to achieve a more realistic evaluation, we also built hardware prototypes based on the FPGA platform born with these 3 SonicBOOM codes. We selected these 4 types of spectral attacks to demonstrate the efficient security of our defense scheme, and we also conduct performance evaluation based on the SPEC 2017 benchmark suit. SpecLFB demonstrates a significantly lower performance overhead compared to SCT and SSE-RV. And furthermore, we evaluate the FPGA hardware resources utilization for SSE-RV and SpecLFB. SpecLFB leads to a lower additional lot utilization of only 0.77% and lower flip-flop utilization of only 0.31%. And finally, let's make a conclusion. SpecLFB limits the scope of unsafe speculative loads that need to be delayed to muscles, which denotes unsafe speculative loads that cause cache misses, and introduce a simple yet effective security check mechanism that works in conjunction with the LB unsafe mask to the line field buffer, preventing the cache refill of muscles. And for experiment, SpecLFB is implemented both in SonicBOOM and Gen5 out-of-order processor, and lead to an average hardware resource overhead of only 0.6% and a performance overhead of only 1.85% in the FPGA hardware prototype experiment and 3.20% in the Gen5 simulation. That's all my presentation. Thanks for listening.